This is part 3, our last part on our series of function transformations. In this video, we are going to apply the first 2 parts, so the parent functions and learning about the transformations, to example problems. So specifically, our goals are going to be able to describe function transformations, to graph transformations of however you think of it, parent, mother, basic functions. And then what we'll do is, given transformations in basic function, we will write an equation for the function. Okay, so just as a reminder, I wrote this big long equation at the end of the last part. A is our vertical stretch or shrink. If absolute value of A is greater than 1, it's a stretch. If absolute value of A is greater than 0 and less than 1, then it's a vertical shrink. B is a vertical translation. It moves the parent function up or down. C is a horizontal stretch or shrink. If absolute value of C is greater than 1, it's a stretch. If absolute value of C is greater than 0 and less than 1, then it's a stretch. We've also got some notes about reflections there. And then D is a horizontal translation, so it'll move the parent function left or right. And I put a note at the bottom. So when you're applying these transformations, you go in order of operations. So you'll do what's in the parentheses, meaning horizontal translation first, okay? The last thing that we do is typically the vertical translation. Okay. All right, so describe how the graph of the function can be obtained from one of the basic graphs, graph the function. Okay, so I do have the graph of the square root of x on the screen. This is going to help us as we go through, but make sure that you understand how to identify the basic function because it won't always be given to you. So in this case, the basic function or the parent function is square root of x. Okay, we go order of operations. We've got nothing in the parentheses next to x. We do have being multiplied by 2. Okay, so this is a vertical stretch. By a factor of 2. And then that minus 4 means that we are going to move it down 4 units. Okay, so the first thing that we apply is the stretch. Okay. So 0, 0 is going to stay as 0, 0. 1, 1, what we can do here is we can multiply the y value by 2, okay, because that's our stretch, so that's going to give us a new point of 1, 2. If we do the same thing here, we're going to end up at 4, 4. Okay, so the green is just with the vertical stretch by factor of 2. And then we have to move this down 4 units. We should keep it red. So every point is going to move down 4. So 0, 0 moves down 4. My new point at 1, 2 moves down 4. And my new point at 4, 4 moves down 4. Okay, so this is what I have. So red is the final answer. Okay, and so now we're supposed to give the domain and range. Let me switch colors here. So my domain is all of the x values. You can get this from the graph or from knowing that whatever x has to be is positive. My domain is 0 to infinity. My range, the lowest y value is -4, and this will go on to infinity. Okay. Example 2, describe how the graph of the function can be obtained from one of the basic graphs, then graph the function. So again, we are working with the square root function as the basic graph. Okay, we take care of horizontal translations first, so moving left or right. So we have x plus 3, so this is going to go to the left 3 units. Okay, and we have a negative out in front, which means that this is going to be a reflection across the x-axis. Okay, so this plus 3 is our left 3 units, and the negative is the reflection. Okay, so first we'll go to the left 3 units, so we move every point to the left 3 units. Okay, so here's what we have, and then we reflect it. So again, it's like folding this across the x-axis and having that green line leave an imprint. Okay, so we'll still have a point here. This will be at -2, -1 now. Okay, and this will be here. Okay. So red is the final answer, is what it would look like. Example 3, describe how the graph of the function can be obtained from one of the basic graphs. Graph the function and give the domain and range. So we have f of x is equal to negative x cubed plus 2. So our parent function here is f of x equals x cubed. And again, make sure you know how to identify that. I have it just on here just because it makes it a little bit easier when we're graphing in this format. Okay, so we've got a negative in the parentheses, so this is a reflection across the y-axis. Okay, and this plus 2 is going to move the graph up 2 units. Okay, so reflect across y. So instead of a point at 2, 8, I'm going to have a point at negative 2, 8. Instead of a point at 1, 1, I'm going to have a point at negative 1, 1. 0, 0 stays. Instead of a point at negative 1, 1, I'm going to have a point at 1, negative 1. And then instead of negative 2, negative 8, I'm going to have a point at 2, negative 8. Okay, and I'm going to draw this the best I can. Not bad. Okay. And then we have to move it up 2 units. So every point goes up 2. Oops. Oh, that's really bad. Okay. Every point goes up 2 units. Okay, so now I have something that looks like this. Okay. Got a little bad in there. Okay. Something that looks like this. Give the domain and range. So the domain is all of my x values. You read those from left to right. So my domain is negative infinity to infinity, and my range is the same, the lowest y value to the highest y value. Example 4, graph the equation y equals 3x squared and give the domain and range. This 3 is a vertical stretch. Vertical stretch by a factor of 3. So you can use a table of values if you want, where we would plug in x as negative 2, so y would be 3 times negative 2 squared would give us 12. If we plugged in negative 1, we would have 3 times negative 1 squared, which would be 3. 0 would still be 0, and so on. Okay, so we can go ahead and graph this. So 0, 0 stays the same. 1, 1 is going to go to 1, 3 instead, and notice it's trying to, it's moving away from the x-axis. Okay, and same thing over here. And 12 will run off the page. Okay. So that is what it would look like. The domain and range. Domain is our x values, which will go, it's going to keep going off, off, off. Okay, so our domain is negative infinity to infinity. And our range, our lowest y value is 0. That's included, so it gets a bracket all the way to infinity. Okay. Example 5, describe how the graph of the function can be obtained from one of the basic graphs. Graph the function and give the domain and range. So I have g of x is equal to 1/3 times the absolute value of x minus 5. My parent function in this case is the absolute value of x. Okay. So this will be this 1/3 out in front means a vertical shrink by a factor of 1/3. So what that's going to do is the graph is going to move closer to the x-axis. Okay, this minus 5 is going to shift it down 5 units. Okay, and so whenever we're dealing with a vertical stretch or shrink or horizontal stretch or shrink, it can be helpful to use a table of values, especially in this case because we're dividing by 1/3. So if we use a table here, let me switch colors. X, g of x. Okay, so if we plug in, and I'm going to plug in multiples of 3 actually since we're dividing by 1/3. So I'm going to plug in negative 3. 1/3 times negative 3 minus 5. This is negative 1 minus 5, which is negative 6. Okay, if I plug in 0, I'm going to get negative 5. And if I plug in 3, oh, this is absolute value of 3. Okay, so this should be 1 minus 5, which is negative 4. And if I plug in 3, I'll get the same thing, okay, -4. Okay, so when you plug in the table of values, it's going to do both. It's going to take care of the shrink, and it's also going to take care of the moving it down 5 units. Okay, so I have a point at -3, -4. Is right here. I have a point at 0, -5, and I also have a point at 3, -4. Okay, so it's going to look like this. So it's going to keep the same general shape. It's still going to look like a V, but it's been it's undergone a vertical shrink, and then it's also gone down 5 units. Next, describe how the graph of the function can be obtained from one of the basic graphs, then graph the function. So we have our parent function of the rational function, f of x equals 1 over x plus 3. So all that we have here is it's going to go up 3 units. Okay, so I'm going to take my points and I'm going to go up 3. So instead of 2, this is going to go to 5. Instead of 1, 1, this is going to go 1, 4. And then this is 2.5. 2, 0.5, so it would be at 3.5. Okay, and this piece will look something like this. And then we do the same thing for the other piece. Okay, so for this one, we've got 2 pieces that we're working with, and make sure you take care of both of those. So everything's going to go up 3 units. So this is going to be at 2.5 now. This is going to be at 2. And this is going to be at 1. So it'll look something like this. And so that would be the baby function that's been transformed from the parent function of f of x equals 1 over x. Our next couple of examples, rather than graphing, we are going to be given a basic function, the transformations, and we will come up with the equation. Okay, so we have write an equation for a function that has a graph with the given characteristics. So it's got the shape of y equals absolute value of x. So that's our parent function, but it's been shifted left 5 units and up 9 units. Okay, so first let's start to build this. We have f of x is equal to absolute value of x. Okay, or actually, since it gave us y, we're going to work with y. First, shifted left 5 units. This means that we are going to be adding 5 to x. Okay, so this becomes y equals absolute value of x plus 5, and do a double check. From what we know about transformations, will this in fact shift the graph left 5 units? Yes, it will. Next is up 9 units, so we're going to add 9 to the end of this to get y equals absolute value of x plus 5 plus 9. This is our final answer, and I encourage you just to look these over and do a double check. Is what you wrote in the equation matching up with what was given in the problem? Okay, next example, write an equation for a function that has a graph with the given characteristics, the shape of y equals x squared, but upside down and shifted right 4 units and up 2 units. Okay, so we have y equals x squared as our parent function. Okay, upside down, so if it's upside down, it's been reflected across the x-axis. Okay, so reflect x, so that means we have y equals -x squared. If it's shifted to the right 4 units, that means that we are going to be subtracting 4 just from x. Okay, so what that looks like is we still have this negative, but now we're shifting to the right. So we put that in parentheses with x, and then we're going to go up 2 units. Okay, so at the end, we add 2 to this. Okay. Thank you for watching. If you have any questions, feel free to reach out to me.